You have a lecture of Professor Timothy.
So in some sense, my talk overlap quite a bit with what Bruce have talked about. But what I want to emphasize is you can see actually from a more clinic point of view what people do to determine the optic property. And actually what I'm covering mostly is covering a simpler method, so-called DC, diffuse reflectance type of method. So I'm going to go over some introductions about the method that has been used. And this is actually based on a review paper which one of my graduate students have done with me recently. And looking at the superficial probe, which based on broadband diffuse reflectance, and also interstitial probe based on the broadband diffuse transmission spectrometer, and some other special method we use during the PDT treatment, of course. So in terms of introduction, the tissue optic properties, as you probably all well know, can be determined using absorption spectrons. That determines the attenuation coefficient and the scattering coefficient. Usually it's a reduced scattering coefficient. And well, broadly it's categorized into two parts. One is reflectance spectroscopy, or the other is transmittance. So one, you can use it for semi-infinite medium, and the other you can use it for interstitial. Of course, you can also use transmittance for tomographies, which I don't really cover that much here. So it's nice that Bruce has covered that very nicely. And depending on the type of light modulations, it also can be separated into a continuous wave, time of flight, or frequency resolved absorption spectrum. And I'll just go over this a little bit, sort of a summary of literatures. And this is by no means a complete list of literature, just a selection of the ones that's important. Broadband diffuse reflectance determines the diffuse reflectance as a function of distance on a semi-infinite medium. And Farrell and Brian Wilson's group initially has developed a formula for this diffuse reflectance as a function of distances. And other peoples, including Bruce Trumber's group, and has also worked out the formula, and they have a very detailed papers on the boundary conditions. It's really one of these are all classic papers. And that formula actually has been refined by the same group to give better expressions, which is actually most commonly used nowadays, these expression. And also, Tom Force's group has expanded it into P3 approximations, so that can allow it to be applied to cases where there's high absorptions. Certainly there's some other method like using Monte Carlo simulation directly to determine that. And in terms of frequent modulated broadband diffuse reflectance, you have heard all about it in the previous talk, using frequency modulated device light source. That will allow to determine not only the amplitude change using CWs, but also give you additional phase shift. And that will allow one to determine these optic properties using even one separations. And several groups have done that, and including Bruce's group, Britton Chang's group, and at Penn, and of course, Brian Wilson's groups. Here is some more recent measurement. And the other method is so-called time-of-flight diffuse absorption spectroscopy, which actually is measuring the photons directly following a pulse laser. So you can actually measure the time delay between each pulses as propagated through the tumor. And Steve Jacks has originally described some of these methods. Mike Patterson has written a paper in the late 90s about a single Monte Carlo can be used to determine the tissue optic property, use these particular methods. And here I have pointed out papers done by an Italian group and also by Lund to use this method to develop a mammography unit that can, do the measurement for breast. And also the Lund group has used it for measurement in prostate during PDT treatment for optic properties. And there's a very nice review papers recently, 2008, by Steve Jacks and Brian Poe, that talk about all these different methods and the theory behind it, and how to derive the equations to interpret the data. So I'm going to spend more times on these, more conventional method, simpler method, which is based on the CW light source. And what it typically doing is introducing a point source into the scattered medium, which will diffuse through this, scatter bond, rumble bond, or through being absorbed by these absorbers. And a diffusion equation, can describe all this. It's an approximation of the photon transport equation. And that allows one to determine the absorption coefficient mu A and the diffusion coefficient, which is related to reduce the scattering coefficient. So these are the quantities one can determine. So light fluence rate can be measured, and that will correlate to, the diffuse coefficient is correlated to the mu S prime and mu A. Mu A and mu S prime is the one has to determine, and also speed of light will be measurable depending on the medium. Light source is here. So there is very well-defined equations that describe this diffuse reflectance in terms of the fluence at the detector site, fluence rate, and also the flux at these locations. And these are the very classic papers, and that describe this equation. And this actually is the one that actually is commonly used. More recent papers that give you a more correct expressions for it. So the light fluence rate is actually calculated as original light source here. This is actually a point source, and the mirror image of the point sources. So basically, the light fluence rate at here is composed of the two sources at this position, and that reason of that is due to this boundary. It's because of this air and tissue boundary. And also the flux is defined, of course, is a gradient of light fluence rate in the z directions where the detector can measure and multiply the diffuse reflectance, and this is the expression for it. So these are analytic expressions, and if one change the distance between the light source and detector, this formula can be used to extrapolate out the mu A, mu S prime, because they have this complicated relationship. Now there's two coefficients, C1 and C2, and that coefficient depends on the boundary condition, as well as the detector type. And I remember last lecture someone asked me whether one can use isotropic detector here. Yes, one can use isotropic detector, but if you use a flat cut fibers, you have an NA that's constrained by a particular NA, and if for that particular condition, you can get this C1, C2 number, which is a function of index refraction of air and index refraction of tissue. But if one use a different isotropic detectors, for example, then you can collect light from all 360 degrees, and you will get a different value of C1, C2, which can be calculated based on these papers. That will allow you to do the same kind of calculation. So in a sense, one is measuring this diffuse reflectance coming out of the tissue. This is a diagram of the instrument, which actually, compared to Bruce's instrument, is very simple, point source, and originally is actually developed by Brian Wilson's group. It's a contact probe, point source, pencil beam coming in, and detector is detecting the signal from different distance, which can be fixed, and going into a micrometers, and a CCD camera pick the signals. And these are the early prototypes that we had been using before, and actually mostly based on Xinwen Wang's work. So you basically can use an array of detector and light source with equal distances, two different early probe. You can also determine diffuse reflectance based on a pre-integral field calibration, and that calibration is necessary because each probe will have different transmissions. So one have to calibrate it in the integral sphere to make sure you have same light coming into the probe and account for the different transmission from different probe. This is a more recent probe developed by Gerald Finley in our group. And it's much easier to use, which is basically a contact probe. You touch on the tissue wherever you want to measure, and push a button wherever the physician is ready to do the measurement, and that the data will be taken automatically. And one can certainly, as Bruce has described before, extrapolate out hemoglobin concentration, oxy-deoxy, and drug concentration, for example, for PDT use. And also you use me theory to model the mu-s prime. So these are the things that one can just extrapolate out. Basically is not only optic property, but the optic absorption spectrum can be separated into different components, which will give you these components concentration. So some of the results based on these, this is one of the protocol which is in intraperitoneal cases. Photoframe, 48 hours. Treatment is using two different wavelengths. 532 is for the internal organs like small bowel, large bowels, and 630 is for the entire cavity. And optic property was measured in 12 patients in various tissues, large bowel, small bowel, peritoneums, and also some of them has tumors. These are special measurements because you have to actually make the measurement before the tumor is resected, and then resect the tumor, and all the other measurement actually is done, I believe, is right before and after for PDT. So here is a typical result for small bowel. So you will see that mu-s prime is reducing kind of smoothly with wavelengths. Absorption coefficient is also reducing, and these are 12 different patients, so you can see there's a variation between different patients, but they have a general shape like that. One can actually, based on that, to calculate the mu effective, which is the square root of mu a mu-s prime, multiplied together, multiply 3. One thing as so these are the, and if you inverse that, you can get the penetration depths. This is what we use to fit this relationship. So we actually summarize based on these results in a paper written by one of our graduate students. And what we can do is, based on these data, to determine the general shape of the mu-a as a function of wavelengths and the mu-s prime, and also determine a shaded area. And this shaded area is 66% of the mu-a is within that band. So basically is to determine a range of optic properties as a function of wavelengths. Certainly one knows there is a spectrum dependence for absorption spectrums, mu-a, and mu-s prime is generally decreasing. It's changing between about 6 to about 16 centimeter minus 1. You can also, this is done by Xin Wan, one of the postdocs in our group. You can also determine the mu-a, mu-s prime for different tumor types here. And this is basically average all these values mean together for all these 12 patients. So you have data for small bowel, large bowel, heart, skin, liver, and tumor. The result is actually quite interesting. You can see that there is a large variation between different tumor types. Liver certainly will have the biggest absorptions, but as Bruce has mentioned, we also observed that the tumor actually has larger absorption coefficient than the other normal tissues for the same similar type here. And effective attenuation coefficient, of course, is showing the same thing. The liver will have the highest absorptions or the lowest penetrations. So these are basically, we calculate these quantities to help us to determine the light penetrations for PDT. This is a summary of the result at this particular wavelengths where we do the treatment. So you can see different tumor type, not tumor, the tissue type, small bowel, large bowel, heart, pericardium, tumor, skin, liver. Measurement is done before and after PDT. So one thing we actually noticed that the tissue optic property don't change, almost don't change at all during our PDT treatment, and that is pretty much across all different type of PDT treatment. We see that same thing. These are tumor is special because we cannot do after because they resect it out. Otherwise, we cannot do the PDTs that way. So we only see it before PDT. So these are basically the summary of the result for our wavelength. So really the conclusion from this measurement is that you have very little penetration in liver. It's about 1 millimeters. And you have decent penetrations in most of other tumors, varying between 3 millimeter to maybe up to 6 millimeters. With a certain bar, this bar is also 1 sigma. 66% is within this bar for the patient we treated. This is a summary of results that's based on some literature studies because we didn't do breast. So this, I'm not even sure I include up Bruce's result, but there is some of these mammography results that's included. And you can see this shape for the mu A and mu S prime, and again the shaded area is the 66.7%, 1 sigma, the mu A variation. And here is what happens for skin. It's a lot flatter for existing literatures, and including the data from our groups too. Mu S prime is always going down like that, and the shaded area is 1 sigma. Small bowel is again, and there's also some measurement in bone that's summarized here. So the next one that can be done is using so-called broadband diffuse transmission spectroscopy, and the method one can use is by introduce a light source into the tissue, and then you do a scan of the interstitial detector at a known distance from the light source. So if one knows the strength of the point source, you can just do one scan and determine the relationship between the mu A, mu S prime, and the measured results. So if one only knows the relative dependence, doesn't know the absolute light fluence rate and the source strength, one can only determine the relative relationship, mu effective for point source. But if one knows the absolute values, then from this amplitude itself, using the amplitude, one can actually separate out mu A, mu S prime. So the device we use here, this is actually mostly applied to prostate cancers, PDT treatment, is we have a 16-channel system, so you can introduce multiple point sources in different locations in the prostate. And then you can introduce detectors and then scan the detectors and to get the light fluence for the known point source, and a very accurate motorized system one can use. So here is what it looks like. So you basically introduce a point source, and I hope that works. And then you move the point source in different locations in the prostate, and then you do a scan from the point source, and that will be used. So the typical result looks something like this. And a scan is very quick. It takes about 2 seconds. Okay, so the data can be fit to the measured absolute light fluence rate per source strength. And that can be used to separate our mu A, mu S prime. And that interface actually was developed by one of our colleagues, Gerald Finley, and published in 2005. And so we actually use this method to determine the optic property in prostate in our treatment. But as you can, you can notice, if you introduce point source in all locations in the prostate, you can actually build up an optic property map of the entire prostate. And that's, this is what it looks like for treatment typically. So we have a detector in the middle and sources in different quadrants. And that's actually treatment, the coordination. But for measurement, we just take the same catheters and introduce a point source into it. And then just scan it with the middle quadrants. So this is the result we have gotten in this patient. You can note there is a very wide variation of mu-A, and changing, from 0.09 all the way to 0.71. So it's a heck lot big changes of penetration in the prostate. And these are the average values in each patient. Okay, so there's a difference in penetration depths. And we actually did before and after as well. There is some difference in some patients that before and after is different. One thing you need to be careful is the mu effective actually is quite similar we have. And the other thing is, after the treatment, when we do the measurement, we're not really guaranteed you're stick the needle into the same spot. You're in the same region. So this difference, even though you see the difference, my hypothesis is in the different point rather than there is a change in optic property during treatment. And we actually have never seen the light fluence rate changing during our treatment. It's very constant, so that's actually indicative the optic property doesn't change during PDT. So this is what it typically looks like for all these measurements, 121 measurements during prostate treatment. We plotted out these calculated distribution for all 121 measurements, and then you can find a mean and the upper and the lower range for this. So we have obtained mean optic property of 0.3, 1 over centimeter for mu-A, and 14 for mu-S prime for the prostate patient we have been treating. So this actually is our mean optic property for our default optic properties at the wavelengths that we use at 730 nanometer. Upper and lower, you can see upper is lower, higher penetration, lower absorption. So mu-A is smaller, and the upper can go up to about 1.5. Again, if you use this method, you can determine the distribution of optic properties for mu-A and the mu effective. Of course, mu-S prime, you can determine that too. I didn't plot it here. But one thing that's interesting to see is the mu-A for the same prostate. Okay, so different point here is different location for the same patient, same prostate. Right up quadrants, so we separate the prostate into 4 quadrants, right, left, upper and low. So you have see different symbols, and some of them is measured before and after. But the key point is the penetration actually changes quite a bit. It changes, at least here for this point, it's 0.1, here is 0.6, so 6 times change, for example, in this particular patient, which really is indicative one have to optimize your light source distribution for this type of treatment because the optic property is changing. And that translated into a changing of penetration in the tissue. Again, I mentioned before, if you do a reconstruction based on the measure point, you can get distributions of optic properties. And this is done in one of the prostate. For us, one advantage we have compared with other groups which try to do non-invasive method by putting a probe in a rectum is we can put needles directly into the prostate. So our results should be used as a gold standard because it's really measuring where the optic property are. The light source and detector is right adjacent to each other. So this is what it looks like. So it actually, these studies potentially can be used as a method to establish a gold standard for, testing some other methods for determining optic properties in vivo. If one can also develop a rectum-based DOT system. And this is all ultrasound guided, so really the same ultrasound system can be used for these studies. One interesting thing is in our group, all this PDT measurement is done based on linear sources. I mean treatment is, we don't use point source move around to treat because the linear source is more efficient to cover the entire region. And we also have to treat a longer, higher fluence rate. We treat up to 150 joule per centimeter square, and in order to do the treatment within less than an hour, you have to use linear sources to cover the entire prostate. So the then interesting question is, so why do you have to put in the linear source and take it out, putting the point source to the measurement? I mean, that's kind of, the question is that possible to just use the treatment source to do the measurement directly? So this is one thing we have tried in the past few years. One method we use is we basically find out the profile of each linear source that we use. There can be different lengths depending on the location they are based on the ultrasound study. So we basically use the treatment linear source to do measurement. And the only difference now is you have lower power light introduced for each individual linear source. Then you have detectors putting, so here D1, D2, D3, 4, 5, 6 is 6 detectors we put in. In this particular case, you have 16 linear sources that's typically used to cover the entire prostate. Okay, this is done in prostate phantom, but so each one you can turn one on at a time and then do the measurement with all these 16 detectors moving inside the prostate. And that will allow you to basically cover every single location if you turn one on, sequentially. And the question now becomes, now what we lose is if we use point source, we can actually introduce a point at different positions in the apex directions, in and out directions. Now we lose that information. And the question is, can we still reconstruct the optic properties? And it turns out that this is the result by doing a simple calculation, just assuming the detector and the light source pair at each locations, their optic property is homogeneous, okay? So actually, let me see. So this is what our model is currently in this one. So you're basically saying that the optic property in the in and out direction is changing, okay? And don't seem to be working anymore. It's probably used up other light. Oh, yes. So here is different. So we basically say there is a different optic property in this direction. And within each 2 millimeter, 1 millimeter, whatever we can define zone, the optic property is same, okay? And then we can do a measurement between this. This is a linear source with known length, and then we have introduced a detector that scan along these lines. And then we match our measurement with calculation. So these are typical what it looks like. In a heterogeneous phantom, we actually use the prostate phantom and deliberately introduce tumors into it. And so you can see actually non-uniform distributed light fluence rate. This is the fit to the measured values. And here is two profile. One is assuming that the introduced the linear source is uniform. The other is the actual profile distribution. And we actually found out this assumption, the two assumptions doesn't make too much difference in extrapolated optic properties, okay? We have plotted out mu A as a function of distance. It turns out that this method is not very sensitive to mu S prime. It cannot be used to extract at mu S prime very well. But it doesn't actually depend too much on the mu S prime for the mu A extrapolation. So we can sort of getting the mu A out. And the reason we can say that is partly based on, we also did a point source measurement in the same phantom. And we see that they agree with each other reasonably well. So these are different locations. You can see we fitted the data and extrapolated optic properties. Two different methods is used. One is using the actual intensity profile of the linear source. The other is using uniform ones. And we actually prefer to use uniform one because these optic property that we extrapolated out, we're gonna actually use that forward to do the light fluence calculation. So if we use the uniform one, we don't even have to characterize each linear source, what is its intensity profile. So we can actually use, assuming it's uniform, and pick up what optic property we got and do a forward cal, which will get perfect agreement. The reason for that is because they have a perfect agreement in that particular channel. And the agreement now is better than 5%. Unlike before, we are actually talking about 20%. And so you can see this fit result versus the actual measurement. They're perfectly in agreement because we make them to agree, of course. And the optic property you get, also these bumps is corresponding pretty nicely. For example, these two bumps corresponding to a tumor that we introduced into the vent. So this is what we have done by assuming you know the two linear source, zone by zone calculation. And we actually used a software developed at the Brian Post group, and to use that software to see if we can use the same data to do a reconstructions. So this is another phantom study. We actually have every single linear source and the detector pair calculated, measured. And these are the data for all the pairs in a phantom. And then we can do a reconstruction. And again, you can see actually the introduced heterogeneity into this prostate. This is the boundary of the prostate that we are doing measurement with. There is slight crosstalk between the two. You can see these, some of them is actually not real. But let me see if I have any. Yeah, I didn't give you what they should be, but we know what mu A, mu S prime should be. The advantage of using this reconstruction is it seems to be actually predicting the mu S prime better than if we just use a single pair between light source and detector. So next thing one can do, of course, is introduce a white light source instead of laser source at the wavelengths. Then you can get the spectrons. So this is the same slide. I'm gonna just skip it. Go to the next one. So if you look at this zone middle portion, there's 5 points, 1, 2, 3, 4, 5, 6 points. And for mu A, mu S prime, one can determine from the laser measurement at the wavelengths of treatment. For each corresponding point, which is 5 by 5 millimeters voxels, you can determine a spectrum for each one by introduce a white light source. And that will allow us to separate different components, oxy, deoxy, hemoglobin. These are actually separation components done by Gerald Finley, one of. And that will allow us to find out a distribution map of oxygenation as well as the drug concentration, 2CAT. Here is one example that shows what is the relationship between total hemoglobin concentration, oxygen saturation as a function of distance inside the prostate, and also the drug concentration. In this case, it's the Lutex that we are using. And you can determine the drug concentration before and after. No, this actually is compared with another method that is also used in clinic. It's a fluorescence-based method, and they also agree with absorption method. Here is the summary results of all our measurements. And also the shaded area is the area where the 67% of the numbers is falling in that region. So what's the use of these optic properties? Well, for prostate, for example, for this case, one actually can use the measured optic property to calculate the light fluence rate. And this, as you can see, is very heterogeneous. And here is actually the geometry of how we did. This is done in vivo. This is actually one actual patient. In this particular case, 12 sources is introduced, and each circle corresponding a zone, right up quadrant, left up quadrant, right low quadrant, left low quadrant. And we have 4 detectors in each zone. So the detector is measuring the total light fluence during the PDT treatment. And now we know the optic property already, so we, based on this optic property, do the calculation and can compare with the measurement. So here is some comparisons in one patient, number 16, right upper quadrant, left upper quadrant, right lower quadrant, left lower quadrants. we can say that, you know, it's reasonable agreement. So the agreement here you can see is 30% maximum deviation, and 31%, and mean deviation is 13%. So we can actually get the 13% agreement between our calculation and the measurement. If we don't use heterogeneous optic property, if we're assuming the entire prostate is homogeneous with a single mean optic property that we use for all patients, we can get a mean agreement to within 50%. At maximum can be over 100%, but that's still, you can do some predictions. Some other method that being used is size-specific, which is head and neck. I think you know, some of you may be interested. So what we introduce here is 2 parallel catheters. We also do contact probe. For wherever you can, you know, access, you can do a contact probe measurement to get the optic property. But this one is kind of interesting because you can introduce that into larynx in areas that you cannot access normally. And for example, in larynx, you can actually introduce a balloon and enlarge it, and then you can make sure there's a contact between detector and the light source. So we actually introduce a point source and introduce a detector into this catheter, and the stepping detector to different locations, and also stepping the linear source using this so-called point source method. The only difference now is now you actually have a semi-infinite geometry rather than infinite geometry. And also there's one complication which may be coming out. That is because in the mouse there's lots of scattering from all the way around, and that's actually why we introduced this black back, because we basically block them all out just so that you have a point source introduced. So this is what it looks like in the bottom. And here is some method. It's a semi-infinite model. Now we also actually have to modify the direct light somewhat. It turns out the direct light is no longer tissue independent. There is some tissue dependence in this particular geometry. But if we introduce that dependence, we can get a very reasonable agreement in phantom conditioning. We did 6 patients here. So the upper one is tumor, post-PDT tumor and post-PDT normal tissue, 2. And the lower one is before pre-PDT tumor on the left. I think, so this is a pre-PDT tumor and a pre-PDT normal. So again, you can see a large range of penetrations, for example, different mu effective changing from 1 centimeter minus 1 to 2.7. So there's a large change. So there is a patient-to-patient dependence. And the main inference now is, of course, the light given. So all our protocol is based on measurement, which means those tissue heterogeneity is already taken into account. So they are given, up to, I think it's 150 joule per centimeter square now. It's escalating from about 40 up. So here's a summary. This is a summary optic properties that one can get, and this reference is giving you the different references. So it's a different method that's being used. So we basically, giving up a table for these optic property variations in patient in vivo. So all the data here is in vivo data, and then that's possible because of the development of this contact probe, and this is really making it possible now. So in summary, we demonstrated the diffuse reflectance system can rapidly extract optic properties in intracavitary PDT or in many PDTs, superficial too. Broadband transmission spectrometer can be used to determine optic property in the so-called interstitial PDT cases. Some other miscellaneous method can be used for head and neck patient, for example, or esophagus. And our conclusion is the mu A for normal tissue is changing 0.013 to 1.6, 1 over 6, and mu S prime is between 1.2 to 40. Okay, so this is a typo. So that's the range for the data we have. And I want to acknowledge all the big groups and also the ground support. In the end, I want to say something about our cancer center. So this is the Permanent Center of the Advanced Medicine in Japan. And here is the physics department. Here is the cancer center. This is the cancer center. And right across is a hospital. And here is a children's hospital right next to it too. So it's really convenient to walk between the physics department and the cancer center. It's really, about 15 minutes walking distance. That's what it looks like. This is the new cancer center inside, night view, and outer view. So the things which is very nice is they also have a research center built right, in the same building. So we have the labs here doing all the lab, and then you can just wheel things down to the cancer center very easily. Okay, thank you very much.
Sorry, I may have missed this, but are you monitoring the property changes during the therapy?
Yes, Arjun's group did most of that. I didn't
You
add
didn't?
any of data, so I didn't do it. So Sophie has all the data.
Yeah.
So she has monitoring during PDT. The problem for this CW is the light, the treatment light will screw it up.
Yeah.
So your instrument will be perfect, frequency modulate. And so Arjun has the one of
And
these
Arjun has
instruments.
one
so the
too,
way, so he's monitoring both blood flow as well as hemoglobin during the entire treatment.
Yes.
So that was done. Yeah.
And what is your
The only drawback I would say is all these are point measurement. So
Right.
you have an image, which would be great.
yeah. And how about for the prostate? What's the status of that worldwide? Is that I see some presentations by a few groups. Do you think that will begin to grow and become more widely accepted?
So I think the only existing PDT prostate is TrueCAT, I think. That's still in existence, going on in France and some of the sites. I am not quite sure that dosimetry is done adequately, actually. I think that will potentially do a disservice to the community if you do not do any dosimetry at all, and just based on the average light. As you can see, these optic property change greatly, and
Yes.
the dosimetry is really changing a lot. So I'm hoping the new ones, with SpectroCure is going to start with BPD. Verdiporphyrin will be exciting one to see, because there the dosimetry is very well controlled with the system. SpectroCure has a
Yes.
fabulous systems that controls the optimize the light, and that is based on the tissue optic property determining in real time.
Yeah.
And that is something I'm really looking forward to.
Very good.
We don't have our Lutex protocol. It was stopped earlier because of the drug problems we have. So that didn't. So we had just finished phase 1.
Mm-hmm.
No phase
Thanks.
2.
Thank you again, Professor.
Okay.